Hello again. In this video I want to talk about why Polaris doesn't move, or better to say why Polaris almost doesn't move, because in fact Polaris does move, but only very subtle and barely visible to the naked eye. For this I want to tell you about the heliocentric and the galactic model we have. Our galaxy consists of hundreds of millions of stars, and our Sun is one of them. And all stars we see with the naked eye are entirely only from our galaxy, from the Milky Way. Our Sun, together with all other stars, rotates around the galactic center. The position between the stars relative to each other stays the same, more or less. Of course, the stars also have some own movement, but this can't be tracked with normal equipment. You need very precise instruments to see this. In our solar system, the orientation of Earth's rotational axis also stays the same. This is why we have seasons, because we have a tilt. And this tilt is always directed to the polar star, or near the polar star. It's the celestial pole, which doesn't change its orientation. It does change its orientation, but only slightly. So it's better to say it almost doesn't change its orientation. So now in December, the northern hemisphere is tilted away from the Sun, and the southern hemisphere is tilted towards the Sun. This is because the northern hemisphere now has winter and the southern hemisphere has summer. Exactly the opposite is in June, half a year later, where the northern hemisphere is tilted towards the Sun and the southern hemisphere is tilted away from the Sun. So it's summer here in the northern hemisphere and winter in the southern hemisphere. This tilt still stays the same. It's only the different position of Earth on its orbit around the Sun. The rotational axis still points in the same direction in summer as well as in winter. There are two reasons why Polaris doesn't stay at the exact same place. And this is because all stars which rotate around the center of the galaxy, in addition to their orbit around the black hole in the center of the galaxy, they have their own independent movement. But takes really long until you see that the constellations are different. And this is only possible with really precise instruments. Another reason that for Polaris not staying at the exact same place is that our rotation axis doesn't stay exactly the same. There is also a movement called precession, which causes the rotation axis to change its tilt. It's not always 23.3 degrees. This is something we may not see with our naked eye, but we are able to recognize this with instruments which are accessible to amateur astronomers, like star trackers. Star trackers have to be polar aligned. So when we use star trackers, these are devices which make a rotation of 15 degrees per hour. They are meant to compensate Earth's rotation, so we can direct our camera to a point in the sky, and the star tracker helps that this camera stays at the exact same point, despite of Earth's rotation. But for this to work, we have to make a polar alignment with the star tracker. And there we see very clearly there is a scope we have to look through and have to point at the polar star, at Polaris. But there we see, for a correct polar alignment, it isn't sufficient that we simply point at the star, because the star is not at the celestial pole. The star Polaris has a certain distance from the celestial pole, or from Earth's rotational axis. You see this crosshair, which marks the celestial pole, and this ring around it. And in this ring we have to put the polar star dependent of the daytime and the year, because the daytime, of course, this ring, you have Earth rotation of 15 degrees per hour, so you have to position the polar star on this ring for the right time. You also see there isn't only one ring, there are multiple rings, and you see this years aside of it. And the reason for this is because the polar star changes its distance to the celestial pole. And for every year you have to come a bit nearer to the celestial pole because of the movement of Earth's rotational axis. For a correct polar alignment, there are apps which determine your position on Earth and the time, and for this the correct position of the northern star, or of Polaris, on this ring. And if you have managed to polar align the star tracker exactly on the celestial pole with this app, you are able to make very long exposures with a camera to photograph very faint objects which aren't visible to the naked eye. You can catch more light from the same point in the sky to make objects visible, and this is one really interesting aspect of astrophotography. There was also a term you mentioned, which was circumpolar stars. Well, and circumpolar stars are dependent from the location on Earth, because these are the stars which rotate around a celestial pole and never dip beneath the horizon. So they are always, I wouldn't say visible, because on daytime they are still above the horizon, but you don't see them. When you are nearer to the celestial pole, you have more constellations around it which never dip beyond the horizon. When you are at the equator and the celestial poles are at the equator, you see maybe both of them. You have no circumpolar constellations, because after 180 degrees they move around. After half a day they also vanish beyond the horizon. And of course you have no northern circumpolar constellations on the southern hemisphere, and no southern circumpolar constellations on the northern hemisphere, because you never see them there. There are also seasonal constellations, and they are dependent, you guessed it, from the seasons. Because of course when Earth is at one side of its orbit and the sun is in this side, you will never see the stars behind the sun, because the light of the sun overshines it all the time, and the night side points in the direction away from the sun. So half a year later you have different seasonal constellations, because you see to the opposite side, and the stars, the seasonal constellations you saw half a year before, are now obstructed by the sun, or obstructed by the daylight, and you aren't able to see them. There's also a difference of a solar day and a sidereal day. A solar day is pretty much what we call a day. 24 hours. The time span between the sun taking the same position at the next day. This is 24 hours. But because we also have this orbit of Earth around the sun, there is a difference between a solar day, a day relative to a sun, a normal day, or a sidereal day, which is a a day or an Earth's rotation relative to the stars. When we look at the sky and see certain stars at a position at the sky, we see it the next day after 23 hours and 56 minutes. And because of this difference, we have every day not exactly 4 minutes, and for 365 days around the sun, this adds up to an additional rotation for a 1 year due to Earth's orbit. However, I hope you enjoyed the video. Thank you for watching and goodbye.